All right, so I have series parallel analysis, and let me move this out of the view of the screen, put this over here, and do this. Okay, all right, I can see all your smiling faces, and I can also see the paper in front of me. Get my calculator handy. And let's see, what kind of a circuit do I want to design for us today? How about we do this? It won't be dissimilar to the one that you've got on your screen. I'm going to do it this way. So I will have a point A, I will have a point B. We will go ahead and make this particular fellow 20 volts. We will go ahead and call this from left to right. Let's say this is an R1, this is an R2, this is an R3, this is an R4, this one is an R5. So while you're copying that, let me see if I can take us off of autofocus and make it static. All right, so that being said, let's go ahead and create my VIR chart. So I must have an R1, an R2, R3, R4, R5, and total. Okay. V, I, and R. Cool. All right, let me give you some resistor values. Let's go ahead and make R1 980 ohms. Let's go ahead and make R2 2 kilo ohms. Let's make R3 1.5 K ohms. Let's go ahead and make R4 330 ohms. Let's go ahead and make R5 equal to 770 ohms. So with that, we should have enough information to be able to put onto our document. So is the focus good that everybody can see the values? Okay, I will reiterate down here, my R1 is 980 ohms. My R2 is 2 kilo ohms. My R3 is 1.5 kilo ohms. My R4 will be 330 ohms. My R5 is 770 ohms. My starting voltage is 28 volts. There you go. Cool. All right. So what was the advice that I had given you on how to get this thing started? Where would we start our analysis?
On the opposite end of the voltage source.
Okay, my voltage source happens to be on the right-hand side. And so the opposite end of the voltage source is over this side. That being said, we need to put our eyeball on this side of the schematic. So let's go ahead and I guess that's an eyeball. Anyway, so we're looking at this particular side of the circuit. And as we look at this side of the circuit, what relationships do you see between components that are on this wire in this particular part of the circuit? Question goes to Rebecca. What do you see there?
R1 and R2 are in series.
Rebecca says R1 and R2 are in series. How many of you agree with that, or how many of you have a disagree with that?
I agree with that.
I agree.
Because what was the definition of series? Series means that there's a common current path, a single current path between these two components, yes? And so since there isn't any split between them, there is no split between them, they are truly in series. So that allows us to be able to combine these two into an equivalent resistance, yes? So again, our process is called circuit analysis. So the process is circuit analysis. Our method will be through redraw, several redraws, and purpose to simplify. So those will remain the same. Let me re-ink this. My other one was starting to get a little faint there.
Mom, my teacher said I can eat this. Yeah.
Circuit analysis. Cool. All right. So now we're going to redo this particular guy. And in the redraw, my recommendations are always to save some space below your original schematic and draw directly underneath your original schematic. And so I will retain point A. I will retain the original R3 at 1.5 K ohms. I will retain the original point B. On this side of the schematic, I now have a singular resistance. And the singular one is now called REQ1. And that was equal to R1 plus R2, which in this case works out to be 2.98 kilo ohms. Is that correct?
Yes.
And then on this side, we retain the original R4. We retain the original voltage source and the original R5. Okay. So now, again, the eyeball is looking at the circuit from this corner as far away from the voltage source as possible. So on this corner, the question now goes to Rolando. Mr. Bolito, so glad you could join us. On this wire that the eyeball sees, what do I see attached to this wire at this point?
Parallel with R3.
Okay, we see this resistor in parallel with R3 because the top of these resistances meet at a common node called A, and the lower leads of these two components meet at a different common node called B. So therefore, these two guys are in parallel. Very good. So we will go ahead and combine these two in parallel. And so I will do another redraw. I will bring in my original point A, my original point B, original voltage source, my R4, my R5, and now I have a new REQ, and we call this number 2, yes? REQ number 2. And REQ number 2 was REQ1 in parallel with R3. And so that means we will have 2.98 K ohms in parallel with 1.5 K ohms. So that being said, just off the top of our head, can we guesstimate some kind of a number for this? Question goes to Pauline. The result of these two in parallel to be a single equivalent resistance should come up to approximately some kind of a number. What would that, might that be without calculating?
That would be 3.4 kilo.
They're in parallel now. Do we?
Oh, I'm sorry.
Yes. What do we know about parallel resistance, total of a parallel bank? That this equivalent resistance must end up with a total resistance that must be
Lower.
lower than the lowest ohmic branch, yes?
Correct. Yes.
Okay, and the lowest ohmic branch in this case is 1.5 kilo.
1.5.
So it's got to be something less than 1.5.
Yes.
That's the best we can say right now, since we don't
Right.
walk around with calculators between our ears that can calculate kilos and such. You can certainly say that this REQ number 2 will definitely calculate to be something less than the 1.5K. So if we put this on our calculator, and let me go hit clear, and let's go ahead and do this calculation. 2.98 second exponent 3, and I'm going to reciprocate that. And I'm going to add that to 1.5 second exponent 3 and reciprocate that, equals, reciprocate, and equals. This is what I end up with. Show me what you end up with.
997.
Great, Rebecca. Almost. Yeah, Pauline is good. Andrew, hold it back just a touch. Gabriel is good. Christian looks good. Rolando looks good. All right. Everybody looks like we're pretty much in there. How's was that Ryan's calculator? How about Andrew's calculator? Working on it. Okay. All right. So we end up with, and we would write down 997 point. What are my last two digits there, Christian?
0.77.
Okay, excellent. It would be 0.77. Is everybody in agreement with that, my friends?
Yes.
Okay, so even though your calculator shows 767.8571, you round off to 997.77. Very good. Okay, so this circuit has taken us from the original circuit through a redraw, through another redraw. Have we gotten to our total yet? No, we're not to our total yet. We're still a little ways off. So we still need to calculate our total. And so if we go to do that, what relationship, again, we're looking at the circuit from this perspective on the side farthest away from the voltage source. What relationship do we see between these remaining resistors, Gabriel?
Can you repeat that again?
Yeah, what relationship do we see between these three resistors of this circuit? What's in parallel with what? What's in series with what?
The REQ1 and REQ4 are in series, I believe.
What's happening with R5?
R5 would be 2.
Okay, you're saying all three of these resistors are in series with each other?
Yeah.
Okay, how many people agree? Raise your hands. Well, you got a bunch of classmates supporting you, Gabriel. Good job. They are in series because there's only one current path. So if I go to mark in the,
Add them up.
if I go to mark in the polarities here, here, and the electrons that flow, you can see the electrons will flow in only one path. So therefore, these are all in series with each other. Now, how would I redraw my final circuit? My final circuit will show here, will show my voltage source. I'll show here. Do I still mark my point A and B?
Yeah.
Anybody else? Do I still mark a point A and B?
No.
No.
No, I cannot mark a point A and B, and let me explain why. Because point A, if you look at point A very carefully, isn't point A sandwiched between R4 and REQ2? Well, if we're going to combine them, that point disappears. If we're going to combine these into a single equivalent resistance or final resistance here called R total, here's my R total. Point A, which was between these two resistors, has been absorbed inside of the single resistor. If you take a look at point B down here is between REQ2 and R5, and that, since they're combined, point B has disappeared. So on the final schematic, this guy down here, there is no more A and B. All we have left is our 28 volt source, and all we have left is the sum of these guys in series. So why don't we go ahead and add these guys in series. Bring this guy back up. And watch how this happens on this calculator as each of you discover how to do and utilize memory calculators. This calculator allows me to, oops, come back here. This calculator allows me to add my previous number by simply hitting plus. So it'll take the previous answer, and now I can add all of the giblets of that 997 and add it to 330 and add that to 770. And before I hit the button, let me ask Pauline, what is the total that you get?
I'm still working on it. Hold on one second.
Okay.
2.82. 2.83
2.83
kilo ohms.
kilo ohms. How many people agree with 2.83 kilo ohms? Let me hit a enter and see what happens here. Yeah, I won't quite get that because this is less than 1,000 and these guys come up almost 1,100. So I end up with a less than 1,000 plus 1,100 should be something less than 2,100.
Yeah, I got 210 also.
So this will round out to be 2.10 kilo ohms. So Pauline, you're adding 997.77 plus 330 plus 770. So Rebecca, do you confirm 2.10 kilo ohms?
Yes.
Okay, Rolando, are you good with 2.10 kilo ohms?
Yeah.
Kyle, are you okay with 2.10 kilo ohms? You guys are on mute.
Yes.
Okay, Andrew, are you okay with that number?
Yeah.
All right. Gabriel?
Yeah.
Okay. So we end up with 2.10 kilo ohms. Cool. Now we finally have a total that we can agree upon that we can fill in on our chart. And this guy will fill in right here as 2.10 kilo ohms. Okay. All right. We still have a lot of things to do, but we've taken the original schematic from 5 resistors to 4 resistors to 3 resistors down to 1 resistor. So have we successfully completed the process of our redraws, bringing us down to the most simplified version of a schematic possible? So far,
Yes.
Yeah.
So now, how do I fill in the rest of these values? We fill in the rest of these values by first calculation will be our master current here, yes? This
Yeah.
one. So we happen to have a voltage, we happen to have this. So on this calculator, I'm not going to use 2.10 kilo ohms. I'm going to use my previous value. So I'm going to do 28 and divide by, and I can push this button, come up here to call this, hit enter. So now it brings it
I
down
got
here to
13,373.
28. Okay, and then I can hit equals. So what do you end up with on your currents? Question goes to Gabriel. You're up.
I got 13.39.
What's my second digit?
9.
13.39. How many people agree with 13.39? Raise your hands. Pauline, what do you have?
I think I'm getting 13.33.
13.33. Okay. How many people agree with 13.33? Okay, got some raise of hands there. So Gabriel, yeah, you shouldn't be off with your classmates. 28 divide by, you can call it 2100 if you want to enter it the fast way.
Yeah.
I'm going to write down what my calculator shows me. My calculator shows 13.35 milliamps. And it's okay if you're a couple hundredths of a decimal place off from me because I'm using all my memories, okay? And then when I do a subsequent calculation, I will be using this amount of current with all of its memories. So as long as we're within a couple hundredths of a decimal place of this number, we should all be good. Everybody okay with something very close to this?
Yeah.
All right, let's see how that current flows in the schematic. So here is negative, here is positive. The current flows here, flows here, flows here, and flows here. So my I total works out to be 13.35 milliamps. Now I'm done with this schematic. I can now take this information up here. When I take this information to this redraw, didn't I previously mark negative and positive, and didn't I previously mark arrows for current flow? And what is this current? This current is in fact 13.35 milliamps flowing through these three series components. How does this, taking this information of 1335 milliamps up to this drawing, help us fill in what's going on over here? Question goes to Christian. What do you think?
You could do a voltage divided formula, no?
Oh, we could do we can do voltage divider. Sure, we could. Yeah, that's certainly possible. Let's see. I'm looking for another answer. Andrew or Kyle, what else could we do? One suggestion by Christian was to do voltage divider to fill in some of this. What's another suggestion that you would offer to help start filling in this? Andrew or Kyle? Based on this most recent drawing right here that I've just filled in this information. Your mic is, you're muted. Okay, now you can speak.
I would not all be the same, would it?
Well, let's see. Would it? If you look at the schematic, what kind of a circuit do I have here, Andrew?
Series.
Series. And what is the
Series.
same throughout a series circuit?
Current.
That they're all the same, right? It's the current.
Current is the same. That's correct. So knowing that current is the same, how does that help us fill in some parts of this? You are correct so far. It is series and current is the same in a series circuit.
So that means
If we found the current for R5 and we have the current for R4.
That was Kyle?
the whole thing. Like,
Yeah.
Yes. So as you realize, this is a series circuit. Current is the same throughout a series circuit. Well, hallelujah. You've just agreed that this 13.35 milliamps is the current that flows through R4 and is
Yes.
also the current that flows through R5. So in this part of our analysis, you have found two original currents for R4 and R5. And we can fill that in. That would be 13.35 milliamps for here. And that would also be 13.35 milliamps for here. So R4's current and R5's current are the same in this schematic. and it is 13.35 milliamps. So 2 cells have been filled in. So far, this is a very, very good step of going from the most simplified series circuit and taking it up to here. And from here, we will take this further upstairs, okay? But so far, are we in agreement that we have discovered 13.35 milliamps is in fact the current that flows through R4 and R5, and that allows us to fill this in. So far, so good. Everybody thumbs up?
Yeah.
Okay, looks good. Okay, now we're done with this as far as current goes. Now let's go ahead and take this current further up. The current that leaves the source in each case was 13.35 milliamps. Leaves the source is 13.35. Leaves this source is 13.35 milliamps. And interestingly, in this drawing, this current flows and does hit node A. What do you think with this current, what would happen to this current when it hits node A? Gabriel, what do you think happens here?
I want to say it's going to travel down to R3.
Yes, that current will travel down through R3 because there's a wire attached to R3. Is anything else going to happen at node A? Is there any other wire attached to node A?
R5. Oh, it goes R1 too, right?
This is, what's it labeled as?
Oh, RQ1.
Uh-huh. So the current splits at node A. That's the point that I wanted, the verbiage that I was hoping that you would use. The current leaves the source, comes through R4 as 13.35 milliamps, hits node A, and at node A it splits between 2 different wires. Part of that current splits down through R3, part of that current continues on through REQ number 1. So how do I determine how much splits in each of those ways? Ooh, that would be a question I'll throw out to Pauline. What do you think? What would be one way we could determine how much is the current that actually flows down through REQ, and how about the current that flows through R3? How
We
could we
could use
find that?
the current divider formula,
Mhm.
where it would be IRX equals
Okay, let me go ahead.
over RX.
Okay, let me go ahead and reiterate that. So we have current divider formula, and we will abbreviate that as CDF. And the general form of the formula was, as you recall correctly, IRX is equal to the RT over RX times your I total. So how do we implement this to find out what is happening through R3? If we want to find the current that flows through R3, what are the values that we put in here? This is the general form of the formula. The general form of the formula will always be identified this way. But we have to understand how to apply that formula to the unique circumstances that we're presented with. So if we want the current that goes through R3, we write R3 here. So current of R3 is equal to, so what do I use for the numerator, the denominator, and the total? How would I set that up? Question goes to Rebecca.
For RT, you would put 2.10 k ohms over RX, which would be R3, which is 1.5 k ohms, times I total, which is 13.33 milliamps.
Be careful with that, my dear. So the denominator you say should be 1.5 k ohms, yes?
Yes.
Okay, because that is our X. X is the unknown resistor, and in this case, we're given that X is going to be the third resistor, R3. So R3 must appear in the denominator. RT, you're suggesting that we should use the 2.10 k ohm.
No, that's not right.
And Rebecca now realizes, no, that can't be, because RT is for the entire circuit. So how do we reconcile, what do we actually use for RT in this formula?
Oh, it's the 997.77 ohms.
Precisely. It was these two combined in parallel gave us a total for the bank. The two resistors form a bank, which is the nickname for a parallel circuit. And the total for these two in parallel came out to something called REQ number 2, which was 997.77 ohms. So that's the value we have to put here, 997.77 ohms, and then multiply by the stated current of 13.35 milliamps. Is everybody clear that we do not use the RT for the entire circuit of 2.10 k ohms here, but we use the RT for the bank of 997.77 ohms? Is everybody clear on that?
Yes.
Why do we use
Okay.
1.5
I'm
kilo
sorry?
ohms? Why do we use the 1.5 in the middle there for the bottom number? Why do
For
we
the
use that one and
denominator?
not the other one?
Yeah. So if we want the current through R3, then we use the value of R3. So here we want the current
Okay.
of R3, so we have to use the value of R3. In a moment, we will look for the current through REQ1, so we will have to use the value of REQ1 in a moment. That's a separate
Oh, okay.
calculation
I see now.
after this. Okay. Okay. So let's go ahead and do the calculation for this. And on this particular calculator, I'm going to recall everything from before. So watch for a moment how things are done on this particular calculator, even though you may not have the same calculator, but at some point in time when you get used to using memory on your calculators, your calculations will be spot on with this. This shows a stack of previous calculations. My first number is 997.77, but don't I have 997.7678571? I have this number up here. All I have to do is cursor up to that number, hit enter, and that brings that number down as the first value that I'm going to manipulate. My equation says I'm going to divide. So I'm going to hit my divide key. So there's slash for divide. 1.5K, I'm just going to key in very simply as 1500. And then multiply, I'm going to hit a multiply right here. Now I'm not going to use the rounded answer for 13.35 milliamps because I happen to have that fully calculated in detail up here. I will hit cursor up, capture this number, hit enter to bring it down, and then hit equals for my final answer. Can you confirm with your machines, as you would do it, just type in these numbers on your calculator, 997.77, 1500, and then times 13.35 milli, do you end up with something close to 8.88
Yes.
milliamps? And as long as you're, like I say, within a couple hundredths of a decimal place, Rolando, that looks really, really good. And Pauline, Kristen, Rebecca, you show me your calculations. Don't worry about the memory thing. I just wanted to take a moment and show you how it's done on a full, okay, that looks great, you guys. All right, so we will have for IR3, 8.88.
8.
Yeah, used the wrong color. Okay, so 8.88 milliamps. Ooh, nice. All right. Now, one more current in this bank to solve, and that would be the current on the other side, called IREQ number 1. So IREQ1 is equal to, and I'll write out this first, this must be REQ2 over REQ1 times your I total. And mathematically, this works out to be 997. 997.77 over 2.98 kilo ohms, and all multiply by 13.35 milliamps. So let's go ahead and see what this calculates to be. .98, I had it here. Yes, no? Seriously? Oh, interesting. Oh, okay, I know. All right, so go ahead and hit divide. 2.98 seconds here, 3, 2.98, 3, and then multiply by this current. Okay, cool. Pretty small. Yeah. All right, question goes to Rolando. What were you able to calculate for that current?
4.47
Okay, very good.
milliamps.
Very good. Enter, divide by 8 times. Okay, so if you end up with something close to 4.47 milliamps, it's pretty good. So how many people have something close to 4.47 milliamps? Raise your hands. Nice. Show me your calculators. Good job. Good job. Good job. Nice, 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 nice. Very well done, everybody. Huh. Rolando, we have to do something about your calculator.
R1 should be the same.
Hold on just one sec. Rolando, I noticed something on Rolando's calculator. Get into your manual and figure out a way to extend the number of digits on your display, okay? Not now, but after the session is over, okay? Because the more display information you have on your calculator, the better you're able to make the correct decisions in rounding, all right? All right. So there was a question from Andrew. What was your question, Andrew?
So since that one was for the two on R1 and R2, so that I should be the same for both of those, right?
Wow, that's
for R1 and R2.
That's a great revelation. You're absolutely correct. So this is what Andrew is saying. We just calculated the branch current here as being 4.47 milliamps. And previously we had an 8.88 milliamps here. And when these two currents combine at the bottom, they will add up to be the total current going back to the source of 13.35 milliamps. But his revelation was this current that flows through this branch of the parallel relationship actually flows through an equivalent resistance. And the equivalent resistance was made up of two resistors in the original circuit in series. So this is what we have. We have the current flowing through here as being 4.47 milliamps. And yes, it in fact flows through R2 as well as R1. So yes, your observation of taking this number on our chart and moving it upstairs to here, 4.47, is in fact a correct revelation. Very good, Andrew. Nicely done. So guess what, my friends? You have filled in an entire column of current just by doing current analysis, okay? So we have done, the process is called circuit analysis. We employed a number of techniques We used redraws as the method, and the purpose was to simplify. We did the simplification, and now we're taking the information back up. The information we take back up in this case is current analysis. So we want to add that to our process. Includes current. I'm getting close to my camera here, so I can't write very well. Sorry. So current analysis. And you're going to find that a lot of your circuit analyses can be done with current analysis. You fill in this column, and isn't voltage easy to calculate now? It's nothing more than current times the resistance, right? So let's go ahead and calculate these voltages. So go ahead and start making those calculations. I'm going to be calling out names in a moment for these calculations. Eight, and then here times, that gives me, and then here times, will give me there, and then here will give me, and here times will give me, all right. So I am looking for voltage across R1 by multiplying the current, this current times these ohms, the voltage. Kyle, what do you get for that first voltage?
I got 4.37 volts.
Okay, that's very good. I get 4.38 volts only because I'm using all kinds of memory, but it would certainly accept 4.37 volts. That looks very, very good. Something within a couple hundredths of a decimal place of this number would be fine. So the next calculation, Andrew, I'm looking for VR2. What was your calculation for VR2?
8.94.
Okay.
Volts.
8.94 is what comes up on my calculator as well. That is a correct answer. Very good. Gabriel, what is the calculated answer for VR3?
13.29 volts, sir.
Okay, so 13.32 volts. You have 0.29. Again, we're within a few hundredths of a decimal place. The calculation is good. I would accept that as being correct. The next calculation, Pauline, for VR4.
VR4 is 4.41 volts.
Okay, I have 4.40 volts. We're good. We're within a hundredth of a decimal place. Rebecca, what was your calculation for VR5?
10.26 volts.
Very good. I got 10.28 volts. We're within a few hundredths of a decimal place. Wow, pretty good, my friends. You did really, really well on this series parallel circuit analysis. What was different about this? What was the same? Well, the procedure is we're going to redraw to simplify. We have done so. Once we get down to here, then we work our way back up, and you'll see each of the examples that we create on YouTube and also previously stated in the week 3 part of, week 11 part of your Canvas will reflect the same methodology. Could we have done the analysis differently? Could we have used voltage divider? Yeah, we could easily have used voltage divider because right here, if you look carefully, we know the current through the series circuit as being 13.35 milliamp, yes? Could we have calculated the voltage between A and B?
Yes.
Yes. If you have the voltage between A and B, you have found the voltage across REQ1 and R3. And them being the same voltage allows you to calculate a current here, which then allows you to use those currents to calculate individual voltages. So there's many ways of being able to complete the VIR chart in a circuit analysis. What I've always found is if they with current paths, you follow the flow, filling in one column, the current column will allow you to very easily calculate the voltage just by using math. Any questions on this circuit analysis?